Cool. And then haven't been able to make some of the other ones.
What class did you got this quarter?
I've got algos, the grad computational biology class, and TAAI.
How is algos?
Algos is easier than I've heard it from people.
Is it 332?
Algos is 40.
Oh. Okay, never mind.
330 for the game. And that was the
Oh, so it's my data structures and I know.
Data structures and parallelism is what it's like called, I think. That is what I understand that. And then algos and data structures and algorithms is the non-majors class of data structures. Yep, I'm a second. All right, I'm Carter. I just joined this year, and I'm going to be talking about GPT. And so I'm actually, it's kind of it's kind of like a type of model almost at this point. There's been GPT, the original one, GPT-2, GPT-3, which are all language models. But a lot of generative language models kind of follow the same architecture. So I'm going to generally be talking about what is GPT style or architecture. A lot of the different models, GPT-3, GPT-2, in the original GPT are kind of clones of each other, just with slight modifications. They maybe repeat something more times, or it might have some reshuffling, but it's you're going to get it if you understand one of them. So yeah, thanks for coming. I'm going to start very high level on this, and then try to go a lot lower. I think that'll be easier for people to understand. When I was trying to learn this myself, it was super difficult because I started at these like fine-grained details and I just wouldn't get things. So, what is GPT? It's next word. Can people see this? Okay.
I mean, do you want to turn on the lights?
I'm happy with. I mean, it's for.
There's only one light switch, so they work
So
that.
everything would turn on.
Yeah.
That's pretty good. All right. So what's GPT? It's a next word predictor, right? It takes in a sequence of expression of text, and it predicts the next word. So with a prompt, it predicts the next token or word. It's really just a fancy version of your phone's autocomplete. So that thing that you have that always seems to like autocorrect to ducking, that's what that is. It's that thing. Except it's a really, really good version of it. So if you, and I did this myself before when I was writing this, I just put an and in the text box right over here. And I saw what it would output. And it outputted the in the middle. And so I continued on. It now had and the in the little text box. And the next word that was predicted is only. So this, what's in here, and the is the prompt. And the next word, that output, is only. And we fed that back in. That's and the only. Press it again. The input, that last output, goes back into that input, and then we predict again. In that nature of it feeding back into itself, and taking its prior inputs or outputs as inputs is autoregressive. It takes in its own outputs, it kind of cycles back. It's like a snake eating its own tail. So you can keep going, right? You could write like an essay using this, theoretically, right? You know, if you can keep on pressing, you keep on generating words, you keep going. And so I did, and you get something really convoluted. It looks terrible. And the only reason why I'm still alive today was to get a job at the hospital so that my mom could go back home to her parents for the rest of the day so that she could. That was just for me pressing the middle button on my phone. And that's pretty much exactly how GPT models work. They do that exact same thing, but they're a lot smarter. You can look at smaller chunks of text, and it kind of makes sense. If you only think about, you know, that's this little bit, out of context, it makes sense. But, you know, you look at more, and it's nonsense. It doesn't have a purpose. It's just kind of rambling. And that's what transformers and self-attention can really help with. So, I said I'd start really high level. This is high level. If a prompt, it goes into this magic thing, and you get outputs, an output word. Then you feed that output word, that last output word, in. You concatenate it, so it's prompt, and then that output, you feed it back in, and you get the next word. And you can keep going. You repeat this until you get some sort of end token that you designated, or you've reached a length that you're happy with. It actually doesn't put out output words necessarily. It puts out probabilities. It doesn't spit out actual words, but it puts tokens or probabilities of what that next word will be. And these all represent a word in kind of that dictionary that you have. So there's multiple ways to decode this. One of the easiest ways is that output that you choose is just that highest, that most likely next word. That's 3D decoding. You always pick the word with the highest probability. Are there any questions so far? Please interject. Anybody's wondering anything, I will not be offended. Feel free.
You happen to know, like, for that last output layer,
Yes.
is it like, what's like the activation function for that loop and something?
Yes.
That's a probability of the loop, right?
So let's go into tokens, because we don't actually feed it in actual words, but machine learning models don't take actual words. It doesn't take A, B, C, and D necessarily, but it needs to take something. So how do we represent these bits of language? Well, the smallest pieces of language that we could use are A, B, C, D, E, F, G, right? Letters, all of the ASCII characters. What do we normally use as humans to build sentences? What are our building blocks? Words. Yes, words. So we could theoretically get all these words and map them to these representation vectors. These could be the chunks that we build. There's also something that is also used called byte pairs, and it's kind of little portions of words, and you can use them kind of in between the two. But it's, it kind of makes sense, but I also haven't gone too far into it. I'm just going to use words for this. It's a lot easier to represent things and talk about it. So what happens with the words? Well, the words, these tokens, are mapped with an embedding vector, right? So the word "the" would have its own vector, which represents its meaning, pretty much. And these vectors can be learned, or they can be used from something else, right? The word "the" has its own meaning. So if you thought about certain things, you could do addition with the meanings of these words. There's kind of a common example. It's like king minus man plus woman. That output vector is closest to queen, that queen vector. Does that kind of make sense so far? All right. It's just a huge matrix of ways. Each word has its own vector. They can be learned or pre-trained, or you can take it from somebody else. So let's see. Provides with tokens. So this is kind of our next step. This is what it looks like. We've got our embedding vectors. So we've got the, quick, brown. In each of these, this is the vector for the, this is the vector for quick, this is the vector for brown. These all go into GPT. Something magical happens. You get your output probabilities, you get your decoder. We've got that already. So let's see what's inside this. All right. So inside, this is GPT. We have our token embeddings, like before. We have our output probabilities. This is what's inside. It's stacks of these transformer decoder blocks, one after another, and then at the very end, a linear layer. So with these blocks, right? Yeah. Let me continue. Inside these transformer decoder blocks, because it's primarily this, in the linear layer is pretty simple. We can understand that relatively quickly. But what's inside these. So these transformer decoder blocks have two parts. It has masked self-attention, and this is the tricky part, and a feed-forward neural net. We following so far?
Hold on, can you go back to the, yeah.
Yep.
Okay, so you're saying there's just a lot of transformer decoders stacked on each other before.
Right. So I think that like in GPT-2 it might have been like 12 in a row. I'm not exactly sure with the exact amount, but it's literally just these stacked up, and then at the very end is a linear layer.
So I might be misunderstanding the terminology here.
Yeah.
But I know with transformers, like encoders and decoders.
Yes.
So is it like you train a transformer model and then just the decoders? Is that what this is? Or is it like
Pretty much. So the transformer encoder decoder. Funny enough, it doesn't exactly. There's a difference between this transformer decoder,
and that?
but but it's kind of the same thing that you've probably seen. It takes in its last inputs like this layer takes in its inputs from the encoder, and then it would go through and it would keep on going until it outputs something. It's kind of the same thing in that manner, but there are differences, which I'll get to, promise. All right. So inside this block, there's two things. There's masked self-attention, and there's feed-forward neural net. This is going to take most of our time. This is just a two-layer. It's a single linear layer with an activation function, and then another linear layer. So let's look at masked self-attention. Yes, repeated a bunch of times. Masked self-attention, it basically on this higher level, it allows these words to pay attention to each other, to look at each other. It allows this word to talk to this word pretty much. Here's an example. Here's just kind of an exercise of what's the meaning of he. Can anybody give me an answer? What does he mean in a sentence? Kind of right. It can't look at its other words, so it's really challenging. And this is part of why self-attention is really, really powerful. He needs to look at what all these other words might mean, because it doesn't. Language is not, or language is so dependent on context, so it needs that context. So yeah, it's really impossible to figure out without the other words. And like, what would our process be as a human in this scenario? We could kind of make a query and compare that query across the other words. So we could have some sort of query for what are we looking for? What might he represent? And we could kind of ask all the other words and check across all the other words what that is. So he probably means, I'll let you all see the words, but he probably means man, boy, or male animal, right? That would be kind of a query. And we check every other word is boring of, man, boy, or male animal? Probably not. We give all these other, every single word, some sort of key. Kind of what does it represent? What are its identifiers? And then we score them. So is talk man, boy, or male animal? Probably not. Is Carter man, boy, or male animal? Yeah. So we'd give these numerical scores. Kind of. We'd see how much they correlate. And then we could extract the meaning from all these words. And we could score them, and we'd say, okay, what's most important to he? Like, where's the meaning from? It could be straight from he, but in this situation, most of the meaning from he comes from the word Carter. So that score means that that value of Carter is represented higher. Does that kind of make sense? So we would add it up and put it in. That's what the meaning of he would be. We would do this for every word. We we could compute a query for it. We could compare it to all the other words keys and create kind of a compatibility score. How much do those fit? How much do they relate? And then we could add up all the values of the words, like what does every word in the sentence mean? What does it contribute relative to their scores? And combine, we could inject meaning from all the other words. That's one of the bigger leaps of faith I'm going to ask you to take. How does that sound?
Are you going to talk about others or either mathematically or statistically?
Yeah.
Okay.
That'll be in just a minute.
Just want to go point more a little bit like adding towards the value. So the value is not what is computed with the query key. That is the third query key value.
Right. So say for the word Carter, there's a couple things that you could take away. On a query, what would Carter be influenced by? Well, maybe like adjectives. So you could search for other adjectives near it, and that would be relevant, right? So that's what the query would be. The key is kind of like what type of thing is it? It's an identifier, male, nerd. And then the values are kind of so it's kind of related. What does that mean? That one's kind of the more difficult way of putting it, I guess. There's another analogy that I've liked, and that's if you're searching through a filing cabinet for information, and you have some sort of query, and on the top of each, in the filing cabinet is a bunch of manila folders, and they have on them little tabs that have a key. And so you have your query, and you go through and you look at everything. You look at the keys compared to your query. And you say, okay, this is what I'm looking for. And you look inside, and inside that manila folder is your value. And then you do that for things, and you kind of weight it regarding the compatibility. So yes.
So what's the difference between the score and the value?
The score is how much does he relate to boring, and how much does he relate to was. The value is the meaning of boring, right? It would be more of that like actual kind of original vector. This is the part that's.
So does the value depend on the correlation of the score with other things? Otherwise, why would the value be the same?
So the value, the key is kind of like identifiers.
Okay.
So
This is a really weird point, because mathematically queries and keys are actually identical, even if we change them. So this interpretation kind of falls apart if you consider the math very completely, because, well, it doesn't fall apart, but it's like,
Which ones are in it?
the queries and the keys are just not connected together. There isn't actually any difference between them, and that makes it a little weird. It makes like,
That
Really
makes
working
sense
out.
to me, but that's not the part that
Maybe my question might clarify that. I'm not sure. So can I ask?
yeah,
So it's like the idea what I got from like the vanilla folder example is that like you have a query which is like a question, like some question you want to answer, and you look into these keys and you see like articles that like you think, oh, this might help me the most because it has the word like, say I'm looking for like some kind of China, this has the word like China or something, right? So look at the value of that, and because that came from like a folder that had high relation with the query, that value is weighted more in some function.
yeah, exactly.
Okay.
Right, if you're looking through manila folders with, you want to know World Cup results in a while back, 2002, you would kind of search through all the manila folders and you say, okay, sports articles, and that might be more important. So you look through it, you take that information from what's inside. You might see World Cup results, and you'll weight that even more. Yeah.
So this is all like within the mass self-attention.
Yes. Yeah, so it's all within that block earlier. I'm gonna move on to the map because I think that'll help make things a bit more concrete. As long as this works, it does not seem to be playing maps already. Hold on.
Did you also pause on the next slide real quick and just go back to the last one?
Yeah. All right, there we go. So that's kind of the more like human interpretation of what is going to be described mathematically.
And you add up a value with respect to the square.
You would multiply it. So if you have, a normalized probabilities.
We did this in class on Monday.
Wait, which class?
Deep learning.
Oh, yeah. This is literally the same type of content as what I talked about last year.
Yeah, and I
But it's for that very differently.
by the fifth time somebody presents GPT-3 to me, maybe I'll understand transformers.
Yeah.
Like by the time I get to NLP,
The problem is that
I need 4 more times.
it's not actually possible. It's not actually possible to fully understand it. Like I've talked to several professors, and anytime I talk to an NLP professor, I always ask them this question: do you think you fully understand transformers? And universally, every single one of them says no, and that no human on earth does, because it's not something that can be understood in an intuitive way, like convolutional networks like that. Because the architecture is just arbitrary. It's just what works.
Yeah.
We have a human interpretation of the keys, values, queries, but they're just a bunch of matrices that get multiplied together, and it creates a pattern that works. Like who knows?
The concept of attention makes sense in terms of language, but like how that's implemented does seem arbitrary.
Well,
That makes sense.
it's implemented, like there's a couple arbitrary decisions. It's implemented in essentially kind of the simplest way that makes sense and works.
Makes sense.
But it's, well, when I say makes sense, I mean seems reasonable, not necessarily like is fully understandable. Sorry, that was.
Oh no, dude, no worries. Yeah, so we can do the same thing with vectors. For each word, we create a query vector. We would then compare those to all of the key vectors of each word, and we get a scalar score. And we do that using dot products. And then we multiply each word's value vector, which we create, by its kind of corresponding score. And we sum all those up together. And that would be the new kind of word vector or output vector. This is kind of, yes.
Quick question, so like you dot product one query and another key, and then another one, and then sum those all up or average them.
Sorry, that's it.
You have the first word, right, and you have this query, and then you dot product it with key 1, key 2, key 3, key 4. Do you add them all up or do you average them?
So you don't add the actual attention. So attention is the computer runs doing that operation. We don't add those up directly. So yeah, it's still a vector of just numbers of attention, and those are multiplied by the values of each word, by the value vectors of each word, and those it's a weighted average of the values of all the words essentially.
I didn't get that last part.
But so can you go one slide more?
I hope that makes. Come on, we'll see. Play nice. Oh shucks.
So each word has a value vector. Well, each word has all 3 vectors.
Yeah.
And we want to do a weighted average of the value vectors based on the computer attention. Because essentially, an intuitive interpretation of that could be something along the lines of like the words having some sort of like this the value that gets like related up to like the next layer. No, I
appreciate it.
I have a question on the previous slide.
Yes.
So the value vector is fixed for each word, right? That one never changes.
So the value vector we create for each word.
Yeah, it's unique for each word.
We create, yeah. So
Okay.
each word has. I'm going to go through that in just a second.
Yeah, I want to just put in a quick sentence. So we derive them from the words
Right.
via a pretty arbitrary like
So
matrix multiply. We just do a thing to them to get the exact.
yeah, it's just kind of like you just decode the word.
that operation is learnable. The part that really seems arbitrary and kind of is arbitrary is how we do it is we just do some matrix multiplies together. We just take the same input and just matrix multiply it 3 different times with different matrices, and yet we just take the same data and recombine it with itself in different ways.
It's for all 3
a weird mess.
or just, are you just talking about the value?
Well, these 3 different things are 3 different projections of the original word.
Oh,
So we take the original word and we do 3 different projections
So
of it.
the query key and value vector for each word is unique.
Those are, what do you mean by unique here?
So like, for Carter and talk, they'll be different. But if I take talk again, it'll be the exact same as that talk.
Yeah, yes.
It has nothing to do based on its,
It doesn't have.
it's based on the word itself.
Wait, what positional encoding?
Technically, so with the version that's described here, also position doesn't go into it, so it can actually tell where
Okay,
we are.
okay, let's
That
take it
comes
back
later.
to Carter, because
Yeah.
you'll probably get to these things eventually.
Yeah, eventually.
Right, that is one of the things that I didn't add yet,
Okay, yeah.
but you're smart, you picked up on it. This might help. So the model for each of those self-attention blocks has a value matrix, a query matrix, and a key matrix. And the word key and the word talk and the word Carter, they all they're vectors, right? So the same key vector, I have that in black, that's multiplied by your query matrix. And the same query matrix is used for this one, all of them. It's the exact same thing with this. It's just a value matrix that we learned. And we use the same thing, it's the same kind of operation. We use, to find this, we would take that talk vector and we multiply it by this value matrix. Yeah, and we do that to get the query, key, and values for each word. And those are all vectors. And those, yeah. Is that?
Yeah.
Okay. And so then we score everything. So we take our vectors and we dot product them. So I'm just using key as the example. We would actually do this for every word. So every word would kind of have its own comparison. But just in terms of key right now, we would take key's query and we compare it to every single key vector. And we take the dot product. And then we get some sort of scalar. And that's our scoring. Then I didn't know how to draw it as well. So this is what happened. But we would multiply our resulting score vectors by each word's value vector, and then we sum them into this final transformed, I said the word, the final transformed vector. So I'll go through this all one more time. We use these weight matrices to create a query, key, and value for each word. And then just for one word, at least right now, we would multiply this query by each other word's key vector to get a scalar. And then we would multiply that scalar, kind of how much that matters, by every word's value vector, and we sum those resulting vectors together to create our final one. How does that sound?
And the score, it says,
Yep.
the score for every word, you multiply the value vector, and you get like multiple value vectors, like 8 or so. Right?
Yeah, so each word has its own, I use S for, like, these are different S's.
Yeah, okay.
So these two are multiplied by each other to get this thing, and then this is added along with all of the other ones. These are all different into this final word vector.
So it's not like a maze, it's still a single vector.
Yes.
It's implemented all matrices.
Yeah, I understand that, but for this one word example, it's like you're not just concatenating those vectors and making this
No.
matrix, you're like actually just summing them
Exactly.
element wise. Okay.
Yeah, but this is just literally a weighted average. Like, because all of the different S's sum to 1 because of how it was computed earlier. Because actually, I think you see this on
Yes,
that.
yes.
There's not that.
Yeah, it will be.
So it's just like an average of the values.
So we would actually take all the scores together and we softmax them, which just kind of make sure that that everything adds to one. Yeah.
So I still don't get, so this is an example for key, right?
Yes.
So the value query and key matrix are unique, like it's for the word key. Or is it?
That's a very good point.
Or is it for the mass self-attention?
For the mass self-attention,
So, okay.
everything gets,
So each one of those mass self-attention has their own query value. Right?
yeah. So
Okay.
boring, for every single operation, it's associated with the same query key value. And so I'm only breaking it down to use key as this specific example. But if I were to do it with was, and do the same thing with was, and I compare this, it would be the same, all these would be the same.
So nothing changes.
Nothing changes. I would use this was query vector to compare to everything else.
So all the query vectors are the same.
The query vector,
The score.
Oh.
yeah, so the query vector,
The score is computed by just the key and the query correlated with the value.
so for each word, we have this word, key, is represented with some sort of vector.
Oh, so that's.
This is represented with a different vector, right? And so when we multiply it by a query matrix, or those weights, we get this talk's own query vector, and we get key's own query vector. And so we don't switch it up when we would like compare this to a different word, or we use Carter's query vector.
Oh, okay, I see now.
Okay. Yeah.
Thank
That's a good question. We store everything, we normalize the scores so that they add up to 1, and then we would sum them, multiply. So this could be done with a couple matrix multiplications instead of kind of this really messy line scribbly thing. I'm gonna try to make it a little bit better. I like doing it with the shapes of things. It makes it a little bit easier for me to understand that everything actually would work in practice. So the input shape is batch size, sequence length, and D model, the dimension of the model. So how long are those embeddings? And the output will be kind of the same. This is actually a live build. Worry about that. But the input is kind of the batch size. So how many sentences? Sequence length is how long are those sentences, and D model is how big is the vector for each word. And those all go to mass self-attention. And so this is the way that we would get our query key and value vectors, is we actually just have our input matrix, which is, I dropped the batch size for now, but this would be a batch of them. It would just mean that we have batch as the first, in the first dimension, or that 0th dimension or whatever. Yeah. Okay, cool. So we have our input matrix, and we do a matrix multiply. I use add because, anyways, but matrix multiply against a query, a key, and a value matrix. And those are of dimensions D model and DK, which is that dimensionality of the trying to think about what is this. It's the dimensionality of that attention, basically.
Which one? D model or DK?
DK. So D model is the length of the embedding vectors, and DK is kind of that dimensionality within that attention model.
So is it like kind of arbitrary based on the design of the attention model?
Yeah, you send DK to whatever you want.
Yeah.
But it's the size that you're resulting the key value query vectors will be per token.
Yeah. So if you only have, if we're going to change it up, but for right now, we can just think of this as, we could just have it as D model, the same dimension.
So if say your D model or like the length of the embedding vector was 10 to begin with,
Yes.
and then you would set DK to 5, that means after it leaves the mass self-attention, key transform would be reduced from 10 dimensions to 5 dimensions. you put like a embedding vector of like 10 into this, but you
Okay.
said dk to 5,
So D model is 10.
and dk for like the query matrix and
Yep.
the key matrix, and they also they have the same way.
Yeah, so this would be TDK.
And then
So-
dk is 5, so then
Yep.
therefore like the embedding vector, the resultant like transformed vector for a word would be 5 dimensions now, or like 5.
Yeah, right.
Yeah. Okay.
Yeah. So then once we have our queries and our keys and our values, can't forget them. We'll push them to the side for right now. We're going to transpose the keys and do a matrix multiplication of them, and we get our score matrix. And that's kind of saying we multiply and we compare those those query and key vectors for each word, and we get something of the sequence length times the sequence length. And that basically means that every word, if we graphed it out, we could have like a row for each word and a column for each word, and we'd be able to graph how much they kind of relate to each other. Does that make sense so far? Right. We divide by dk because when you do dot products, it can make the sizes really wonky in those, and the variance really screwed up, I think. So you have to kind of do this to normalize, but we don't really have to think about that too much. It's just a dot product mapping thing. And then we take the softmax, and what the softmax does is it basically makes sure that all value, a couple of things. It makes sure that the sum of all values will be 1, so we can use them as probabilities, like percents. So if it's this function that does this. My thing is disconnected. Any questions so far while I'm waiting?
I never really understood why, like, you're gonna transform or transpose your keys, why you don't just structure them differently.
This is some
Yeah, it's just
because typically, like, you could very easily implement it where it internally isn't like that. Just
Yeah, okay.
yeah.
Maybe it's just
I have a fun question for you.
Yes.
What would happen? So, what would happen if you screw with the score matrix by setting a column? Every value in the column is manual thing.
Well, if you set them all to the same value, it would.
Let's make a column, not a row.
Okay. Well, it basically would mean that one word would be blacked out, right? So it wouldn't pay if we set all the scores. Kind of how much does it? If we said that one word does not correspond with any other words, it has no relation whatsoever, it would mean that, yeah, no, I wouldn't pay attention to that word if I'm reading it, right? The other words don't pay attention to it. That's what that score matrix is how much should the words, or do the words pay attention to each other? And that's actually going to be important later. Yeah.
I think I missed is, can you just see amount of tokens?
It's kind of the sequence length.
Yes.
So,
Okay, yes.
Yeah. Thank you. Yes.
Where does the value matrix come from?
So the value matrix, we're going to move back a little bit. The value matrix, let's see, it comes from here. We have a, this isn't the same, this is like a value weight matrix. And each word kind of is multiplied, each word vector is multiplied by it to get its word value, or word kind of vector, word value vector. And but instead, we can actually just do that with matrix multiplication, where we can get an input matrix and multiply it by our value weight matrix, and we get our values. And we learn this through training. Does that make sense?
Sure.
Okay.
You learn it with a neural network and a magic.
Okay.
I think that's the answer.
Yeah, I'll try to make it a little bit less magic. That's my goal. But ask me later if you want. So, anyways, we get our scores, and our final thing is we use those scores, and we take the matrix multiplication between the scores and the values, and we get our final output. This is our, this is our output. It's of the same size or shape as before.
Oh.
Yes.
I may have missed it.
Yes.
Why is there a divide by root of DK?
Okay. With the I have not taken linear algebra, but I believe it's because if you have dot products of longer lengths, they can get bigger. The variance can grow greater. So you want to keep it with the same thing. So you have to kind of normalize for it. So
This doesn't really do anything because if you divide by DK and then do softmax, like makes a little difference. But ultimately, so the reason the original paper cites for this is that so their actual thing is that we suspect that for large values of these of k, the dot products of a large magnitude pushing the softmax function into regions where it has extremely small gradients. So what that would mean is that it's not that it can't work, it's that the model becomes hard to train for arbitrary weird mathematical reasons that nobody cares about.
So DK basically just like break those numbers down, because higher numbers might.
I also believe that if the differences are greater, it'll mean that some of the scores afterwards, instead of being kind of more rationed throughout, instead of them, it's going to be a lot more peaky, right? One score might be much higher than all the
Well,
others.
so if DK is really big, shouldn't it smooth it out?
Well, if we divide by it, yeah.
Oh, yeah.
Yeah.
So, wait, lastly,
No.
You're probably right, but it doesn't matter.
Yeah,
Right now.
honestly, the decent paper really doesn't matter because the way it actually probably went down is they trained the model and they were like, somebody was like, wait, what if we just try this? They did it and it worked slightly better. And then tried to justify the reasons why they did it later. Like,
Yeah.
that's how this usually happens.
you turned it into like the matrix stuff here. Where in like your original example of actually really to understand like, the other one, like where you went like word by word and you focus on key, where is that division being done? Because I don't think you
I did not do it yet. But it would be like right here, and then after we get all of these, you divide them by the number of words or tokens.
so this each score will be divided by the square root of DK.
Yes.
Okay.
Yeah. That's the way you do it here, but I didn't put it in. Don't worry about it. Yes.
Is it, so the rows and columns of T, so like say 3, 4 corresponds to like the relationship between the third word and the fourth word.
Yes.
So what is the diagonal mean then?
So
It corresponds to itself.
right. Yeah. Exactly. So how much does the word correspond to itself? Right.
Is it still got a score?
Yeah. Well, some words kind of exist on its own, I guess, or like their meaning. They're really dependent on their own meaning. They aren't going to take as much from other things, I guess.
Yeah.
It's like key. You need to go find
Right.
like where to find
Right.
club or like club. Just kind of
Gotcha.
Okay, something you should keep in mind is that this alone is not sufficient for a language model. It needs like several more layers in terms of, well, first it's multi-headed attention, which hasn't covered yet. And then it's also, there's like dozens of layers of these with lots of residual connections and sure. It's like, this is just the core architecture that is being used. Trying to reason about exactly why it works is a bit of a.
Yeah, well, I'm just trying to
I
understand
think that there's value to
There is
yeah.
So then it's like, is it reflected across the diagonal? Is it the exact same? Does that make sense? Because like 3, 4, and then 4, 3. Yeah, would it be symmetric?
Wait, what are you asking about?
So like 3 to
No.
4 is the relationship between the third word and the fourth. But 4, 3.
So the relationships are not symmetrical though, because it'd be the key matrix of the third word. Sorry, it'd be the key vector of the third word compared to the query vector of the fourth word, or the key vector of the fourth word compared to the
So
query.
it's like
That's the
order.
asymmetry.
So it's like queried and key.
Yeah.
Right.
Okay.
And you can think about it like key really depends on the word.
Oh yeah.
Carter, but Carter doesn't really depend on the word
Well,
key that much.
it could if
It could be better, but yeah.
yeah, if it's
I
relevant
see.
for a language model to
Yeah.
identify usages of or references to a word, there could be a different kind of dependency going the other way where Carter would, well, some aspect of Carter's meaning would depend on the word key in terms of how it's being used throughout the sentence. So it's a whole mess. It could be both, it could be neither. It's usually all of the above.
Yeah, so at the end we have our scores, we normalize them, and then we multiply them by our value matrix. So what does that kind of mean? And we get our output. It's transformed now. Woo! So we can also write it a lot easier like this. Query matrix times the transpose key matrix. We divide it by that kind of normalizing value. We take the softmax of it, and then we multiply it by this value vector, or value matrix, sorry. It's kind of a pretty easy, it's like only a couple lines of code, honestly. Move on. All right. So multi-headed attention. We don't actually really do that necessarily. Instead, we do a couple different things. Instead of just taking this entire huge matrix and dumping it in here, and this one and dumping it, and that one and dumping it, that doesn't necessarily, we can do more. We can get kind of more dimensionality in more space with this. So what do? We split it up into a bunch of smaller parts of these matrices. So we get this kind of the same way, but instead of being the full embedding dimension, we could split it up. In this example, I used 4. So there'd be H heads or H matrices, and then they would be of the shape T, and then D model divided by H. This whole thing used to be D model, but then we made H of them, so they're H times smaller. Or we could have it as a shape H T D model divided by H. That clear so far? And then we plug all of these into their own attentions, their own kind of attention functions. So we take the first one from here, and we plug it into its attention. And we take this one, we take the first one, and that would be its own attention function. We'll deal with the outputs in a moment, but yeah. And we take the second of each of the query key values, and we put it into its own attention function. And we would do it for all of them. So we would have H attention functions, or H attention heads, as they'd be referred to. Yeah.
So I am confused whether we're taking like the original we had Q as one matrix. Are we splitting that up into different matrices, or are we like generating new Qs for each attention?
Yes.
Okay.
So we're splitting it up. It literally would just be we could use the exact same thing from here. This is the exact same thing, except we split it up. We would just like slice it.
Okay.
I'm assuming there's some animation at the end to
Yep.
make sure the dimension doesn't reduce by 4 more than many times. But if you're just splitting it up and not like recalculating different queries and keys, and then you recombine them in a proper way, how would that change it?
So it's probably one of the things, and I'll steal a page from you, where not everybody will know, but exactly everything. But my guess would be part of the say the couple. I guess if you have your word embeddings, that first position in that embedding might mean something. And they'll mean kind of different things. If there was like the king, queen, man, woman analogy, there might be like one of the positions, like the first position, might be how masculine something is. So if you split it up, you can get more dimension.
Oh wait, because it's when softmax gets less things. So in that sense, because like each.
That'd be great.
An easier way to think about this might be that we just do the attention operation each time completely separately. We just redo it with a new key matrix, well, not new, but separate key query and the value matrix for generating the vectors.
So the generation matrix changes.
Well, yeah, we just have, instead of one generation matrix for each of those 3, we have H generation matrix.
Oh, I didn't know that was the case. Yeah. So it's not just the exact.
It's mathematically the same.
Well, it's mathematically the same operation, but with different
Okay,
matrices.
so like, when I say query matrix, I mean like a query generation matrix. So the query generation matrix changes for each of the heads.
Yeah. So,
But you also split them by length for some reason, which I mean,
You would do one or the other.
oh wait, sorry, now I'm a little lost, because like, I'm going to generate the query vectors for each word. And now, then, before it was like, oh, simple, you just multiply it by this query generation matrix, and you get this new query vector. Now you have, H query vectors, each one of length, d model over H, right?
Yeah. So
For each one of those, do you have a unique, like a different from the others, smaller query generation vector?
right. So we have this query matrix.
Yeah.
And that gets this. You know, the thing that we're talking about right now.
Yeah.
We could split this. We could take the first 8 of DK.
Yeah.
And we could, or the first 4th, and we could have those be it. Or we could have 4 of these.
Yeah.
And the output would be, instead of DK, it would be DK divided by 4 or divided by H.
That the latter one makes sense as to why it would result in like unique behavior for multiplicative attention.
So
the first one doesn't make sense. Why?
it's just mathematically identical if you dive into the details on exactly how you cut up the matrices. You find that what it effectively ends up being the same elements. You just literally depend on the same numbers. The easiest way to think about it, in my opinion, is the computation being worse, but it's slightly easier version, where it's just we quite literally do the entire scale multiplication operation, but separate. You just do that operation separately with different things. You just have H separate potential operations.
That makes sense for sure.
Right.
So I'll trust you guys that it's like mathematically the same,
And
split it afterwards. So
Yeah.
yeah. And last question is like, I know that there's a softmax in there somewhere.
Yes.
And I'm curious as to how, like, when you softmax it, it takes into consideration, you know, the size of the other elements that will scale it accordingly to result in like a probability distribution. So if you have smaller vectors, how come the softmax doesn't like mess with things? Like, you know, so they're mathematically the same to either have different query generation matrices and split it up after. But with where the query matrices are smaller when you do multiplicative attention. I'm sure. All right, well, in this case, because it's being split up into like smaller. So the query generation matrices are actually smaller than like the big one that we went for to a single head.
Yeah, we can kind of decide whatever we want. Like at the end of the day, we can kind of scale up and down on the dimensions. I put the dimensions here because for me it helps kind of solidifying matrix multiplications and being like, oh, this is the same as like doing the vector thing a bunch of times. But yeah, you can do arbitrary. So yeah, we have these, and I'll try and go quick so that I don't keep people for here long. But you have your different heads. In each of the heads output something of T D model H over H, and you have H heads. So well, you can concatenate them into H T D model over H, and then you could reshape them into T D model, and then finally you put it through a linear layer. I think I'm not exactly sure why, but that's what was done. We'll go over it later. But
the output of attention.
yes.
Okay.
So it's the output of the smaller attention.
Yeah.
Right. And it just allows you to kind of look at different subspaces where it can pay attention to different things. All right, so we've got most of the thing down. Masked attention, masked self-attention. I'm lying a little bit, but I'll try and get there real quick. The feed-forward neural net is it's just a neural net. It has it's a linear layer of ReLU, or I think that they use like a Gaussian error something, and then linear shape. So it keeps it to the same shape. It's just a linear layer. Full model. So you can walk through kind of how it goes. You get your words, and you convert them into tokens. These embedding vectors. words are batches of words. The embedding matrices are shaped dvocab, dmodel. That's my name. That's not the dimension. So the token, now you have something of the shape batches, sequence length, dmodel, and yeah, all of the inputs and outputs generally, at least in this version, are going to be batches TD model. It's the same thing, it's kind of nice. But I'm sure there's other architectures where that's different. I wouldn't be surprised at least. The final linear layer at the very end, not in here, but there's a bunch of, it runs through a bunch of these decoder blocks, which we've gone over. And then after, at the very end, right before it puts it out, it has this linear layer. And the linear layer is of size dmodel, dvocab. So when we take the matrix multiplication, it ends up being batches, sequence length, dvocab. So it kind of, it has those output probabilities. There probably is, yeah. Losses, cross entropy loss between current word and the next word. So if your input was the quick brown, like you're going over that phrase, a quick brown fox, the output you want for the would be quick, and the output for quick would be the next word, brown. The output for fox, or for brown would be fox. So you compare the probabilities. I believe, I'm not as sure. I think that it was cross entropy between. I'm not sure if it's between those output vectors or if it's like a one-hot probability thing, but yeah, I don't think that's as important. I think that people can figure that out. Training examples real quick. We can make kind of XY pairs almost from this. So if we had the quick brown fox jump, or jump, I don't know. The X kind of value that we could think of would be, it would really be this. Would want to change it to jump, but it would be all of this. Would try and predict the next word. So jump kind of follow like this. Does that make a little bit of sense? All right. But there's two issues. The first one is, okay, like, what if you want to start? How would you start something? You know, we don't have anything here. We don't have start. So we actually have a start token that we inject into the very beginning of our training examples. And when you're doing inference, you start, if you wanted to just kind of ramble from nothing, you would start with that start token, and you can define it. There's different ways to do that. You can pad with them or do different things. There's some special tokens. I'm almost done, promise. The other question is, if we're training it to predict the next word, and it can look at all the words, wouldn't it just look at the next word and choose that to be it, right? Yeah, right, with what I said, yeah. So we need to not allow that to happen. So we're going back to this real quick. And we just created our scores. And we could imagine it would score, you know, that next word pretty highly. It would want to do that because it knows that's what it's trying to do. That's a pretty easy mapping. So instead what we do is we set the scores to negative infinity, like was asked before. And then when we do the softmax, that probability, that softmax score is going to be 0. So it will pay no attention to that when he, in none of these words, can look ahead and predict into the future. It can't see later in the sequence. Does that make sense?
That's for training.
Yes. Thanks.
So this is kind of like, it ends up kind of glitching. So there's like a couple ways to do this. This is one of the ways to do it.
Yeah.
It's kind of just like, it just needs, the thing is that this architecture ends up giving you essentially something in the same shape as your input. So you need to somehow kind of maneuver it into giving you a nice looking output.
Yeah.
That gets even weirder with the image transform. transformers or vision transformers. Like people have tried a bunch of different things for it.
And then the final points, there's layer norms throughout the blocks. That just kind of makes sure that things stay stable and gets expected-ish values. There's residual connections between blocks, within the blocks, not between the blocks. Not going to go too deep into that. The other thing I did write down is that there's a positional encoding injected into these tokens because, as you mentioned before, we're passing in these giant matrices. It's not in order. It could just, it could, how does it know the order of the words? Well, we have to inject that in somehow. I think that there's a couple ways of doing that. This mainly like an embedding or like positional embedding matrix.
So cosine. The details don't really matter.
Right.
But there's two ways to describe the original paper. The first is simply to just have a tradeable positional embedding.
Yes.
And that's the easiest to understand. But the one they actually are using is where you just have some kind of mathematical formula that derives on certain dimensions
Different frequencies.
just a bunch of different frequencies that align in ways that lend well to the whole being able to learn positional stuff from them. It's kind of nonsense, but it generalizes easily around that way.
The big thing is you need to do something.
The details don't matter, but
Yeah.
something's done.
Yeah, thanks. I appreciate it. Any final questions to wrap up? I kept you all a little long.
Do you mind a difficult question? Oh,
Sure.
First of all, I was saying,
Yeah.
it's a really good presentation. Like, this is way less stuff than what I did last year.
I wanted to try and get it intuitive.
Yeah, if any of you remember that, like, well, I don't remember. That was but
One of my first introductions to Transformers was actually watching.
oh
Yeah.
So, it's our highest viewed video.
yeah, let's go.
So I could cite you on this. Yeah.
Thank you. But so it's something I've been thinking about more
Yeah.
recently, but going back to you don't have to lose your side,
Yep.
but going back to like the actual words that are being shown, we have like some sentence, we have the word feed in it, and that attends to other words. But after the transformer operation happens, those words are all remixed. So what meaning, if any, is there to applying the key query value of another scale of our attention to all of these jumbled up versions, all the tokens? Like, what use is there in having these multiple layers? What do they actually end up doing? Do you think there's an integral interpretation that you can see for that? This is like a really hard question.
So
At what point do they get jumbled? It's like,
Well,
after
yeah, but it's just like essentially the attention operation takes in a set of tokens and all a set
Thank
of
you, guys.
tokens.
Thank you so much.
Great.
It takes a set of tokens, well, 10 token that is, and creates something new with the exact same shape, but just some kind of recombined version of all of it.
Yeah, like what's here is kind of screwed up right by now.
Well, there's some other side you had that defines shapes, and you can just see that after the tension operation, just all the shapes later on. It's pretty far.
Okay.
It's very far actually.
are you still asking the same question that you just said?
Yeah, it's a okay. So the problem with this question is that it's
Yeah.
actually a question that is quite literally impossible to fully answer, but it's really interesting to talk about.
So here's what I feel. Is I think that sentences in the way that we have them are kind of a block, right? Even a paragraph of text is more of a chunk in the way that we interpret things or we understand things. It's just a whole thing, but we process them often sequentially or in bits and pieces, especially with AI and language models. I think that we have to break it up. In reality, what goes on in our head is we read these tiny things and we read these characters and we put everything together. I think that part of it would be that one of the first layers might be combining everything into a bit more of a, would be combining everything into one kind of block or one kind of chunk of text, or injecting more meaning into all of the other words, kind of making them more like holistic a little bit, is what, and then it kind of iterates on that, and there might be more stuff going on. I'm not sure though.
Yeah, I kind of agree with that to a very extent. Like intuitively, what I would say is like if we have the good brown fox as just a sentence, when you hear that, when you hear the word the fox there, it's in the context of the good brown fox. So in your head, it's likely that there is the word fox kind of as a foothold for your brain to assign meaning, but that meaning is going to be some kind of recombination of the entire sentence and its in context meaning. And that's kind of similar to what transformers end up doing. They end up essentially taking that sentence and reassigning meanings and iterating on making them have the more and more different meanings that end up somehow arriving at something.
You know how you have these written, or so, I don't want to interrupt you, but so you have like the original, like the word, right? Yeah. But actually what's interesting is you embed it into this vector space. The thing is, like, if you think about that process itself, like taking the word and giving meaning a vector space, because everything done in a transformer is done in some way, transforming it with relation to other words that are also, you know, related in that vector space, you could say that some meaning is preserved because you're, you know, obfuscating it, right, somehow, but it's all done with multiplications and multiplication additions by things that are also in this like meaningful space.
Yeah, that's actually exactly what it is.
Yeah.
Because we have to have the original vector space, and the value matrix just produces a projection of it.
Yeah. So,
So,
yeah, exactly.
So that all the value vectors are points within the a projection of the original embedding space. Those are recombined, and just adding those up, you end up, or doing a weighted addition of those, you necessarily end up in something kind of within the same, or within a very related vector space.
I'd be interested to see if like if you kept the dimension of the embeddings the same and didn't reduce decay. You took something in the middle of the transformer layer and decoded it based on like how it was encoded, like it originally encoded the word. If it would like spit out something that was like
in the middle of the transformer layer, or
in the middle of
like
like
tension,
when you
like at the start,
or transform the word heat, right?
So the first transformation, or like let's say 5 to 10 transformations.
First transformation, you decode it back into a word.
Well, that's a little bit because I mean, I guess you just have to reverse things.
It would be close to E though, right? Because the attention that a word pays to itself.
The problem is that there's no reason for the resulting projection to actually have any sensible meaning in the original.
Okay, you're right.
You have to just, I guess you just have to reverse the projection. That might be feasible. Yeah, I could try that.
It's just interesting to think about it.
So yeah, like it's possible you'd end up with you might be able to end up with like a sentence where any pronouns get essentially replaced with a more detailed version of what we're talking about.
It's like all the keys are replaced with like Carvers. Maybe
Or like maybe if there's a car in a sentence, and then there's the word it refers to the car, maybe it'd be like car instead of it. It would be but the problem is ultimately the fact that there is a projection, so you can't just directly take what you get. You have to like unproject it, which is a thing you can do, but it's like not that simple.
So what I'm trying to figure out is like, what I'm kind of understanding is like, okay, let's say we have Karl Marx wrote like the Communist Manifesto, and it's like, why can't you just like understand what that means the first time you read it? Why do we have to be talking about it and passing it on to these other transformer decoder layers like throughout? Like why do we keep needing more people to read the same thing and like convolute the meaning and then trend like, you know? So that's kind of what I'm understanding is like why we have more transformer decoders. But I guess like the question is why can't you just one shot? Like with one trend, is it just less likely?
I think it's just like, I think that it's just not like implementation impossible, right? Like you could have an MLP that approximates any function and understands everything perfectly.
Right.
Right, if you make the layers big enough. theoretically you train them to be like that could theoretically that's not feasible.
Yeah.
I think it's something similar to that.
It's also like a training problem because the level of data necessary for an infinite width, infinite depth MLP just doesn't exist because they're just overkill on all possible data. So this is introducing something like a bias of just like do a restricted version of that. So we have no idea exactly why these restrictions end up making it so effective.
That is a good point. And like part of the reason why it's kind of funky and difficult to understand is because, at least for me, when I was trying to figure it out, is because like how the fuck do you train this thing? Right? Like that was part of it. I'm like, is this really gonna work? Like, is this really gonna make sense? What are you looking for? What are the why target values? So that was kind of like difficult and like was mentioned before, if we're going for images, like that's even more difficult. So I think, I don't know, part of that might be something interesting that I read. Somebody compared transformers to a attention mechanism as basically allowing you to have nodes that can talk to each other. And they can, send out requests. Hey, I need a male name. I need a man, boy, or male animal. And it can send out that request. And another node can be like, yo, I'm broadcasting a male name. And then it's like, oh, sweet. And then this guy's like, okay, yeah, I got you. It's Carter, right? He's born. And, that's an interesting way that I saw it being talked about, is that you made this, it's a bunch of nodes that can communicate with each other, is what the tokens do. That might be more so on in the later layers, where it might have more complex and less easily decipherable things. But it's also kind of I've also heard it mentioned as a differentiable kind of computer, where it can do some computer-ish things.
Yeah.
But yeah.
I think I don't know if we heard that information from the same place or not. Probably. But the location where I heard that is somebody kind of referenced how some previous events have tried to use systems where like we generate sort of like, I mean, if you consider the key and query stuff, that's almost like a little table. Like if you have a database, if you can create a key for something, then by that key you look up. The thought product seems like a pretty sensible thing for the vector space and have a key be in a vector, then just getting something with the same angle is going to correspond to that.
Right, in some sense, yeah, exactly. Especially with the vanilla folder analogy. It's like, yeah, it's like a differentiable lookup table. Yeah.
Yeah. So instead of actually just picking one, you just kind of pick all of them at once, but different amounts of each thing.
Yeah.
If there's interest, I could do a deeper dive into transformers on transformer circuits. The topic recently published. Well, I said recently, that was like this point. Well, half a year ago, maybe. Oh, a year ago, actually, yeah. The topic published deeper dive into transformers, where it's like a different interpretation of it that kind of gets more to the core of what exactly, like what is it that they're actually doing between vectors. When you really talk about like transform the words into, they transform an embedded of the space into an altered version of itself that somehow has more useful meaning. But can we think about that in a little bit of that way?
Yeah, I mean,
There is another way.
I think I could learn more about embedding, wording that.
It looks just like simple thing.
Wording this, whenever we talk about transformers, we've done like twice now, right? Both times like those topics have been like brushed over. So we can like that.
Like also just do like a really simple one. Literally just, I mean, you should definitely read about Roland's like blog post on order representations. That's where I personally did it. Oh, like that was pretty small. I'm sure later.
I had I guess a theoretical question. Like, if you take the transformer, takes like those three vectors, or the three matrices, the query, the keys, and the values, and if mathematically, if they're just the same, you just dot product with it. What if you do 5? Like, what if you just do any amount of odd numbers? Because you need like an odd number so you get the right shape.
What do you mean by the same?
They're just matrices, right? They're just dot product.
Right.
So what if you just add more and more and more?
So that's kind of a decent point where there's GPT.
And you're not like labeling them as queries keys. Where's that?
Oh,
Once
okay.
where you have like
Oh,
an add
yeah,
symbol in the middle.
Oh, yeah, so if you have multiple matrices, because these are linear operations, it actually can be re-expressed as just, so doing 2 matrix multiplies is actually the same as doing 1 matrix multiply. So,
Depending on the name.
well, because if it's literally just 1 matrix multiplication,
Yeah.
you can just re-express 2 matrix multiplies as 1 matrix.
Right, okay.
So it has
Oh,
non-matrices as well.
Yeah. So if you just add more, you're just being redundant.
Kind of,
Yeah.
yeah.
I guess.
You'd just be wasting compute.
Because 1 matrix can be
Because-
matrix.
Because what matrices are is a projection of the vector space. But
Right,
then you just take
right.
that and reproject it. That's still just a projection.
You would just add an intermediary.
Yeah,
one
you don't
for
add
another.
anything to the space of what you can project to. Now, it's possible it could work better due to some weird quirks about like because then it would have different gradients.
More training.
Well, maybe it could be like there could be some gradient screwery somewhere. You could put what you could do is you could put a nonlinearity in between. So you could do 1 matrix projection, then a ray loop or a sigmoid or a 10H, and then another matrix, actually 10H, and then another matrix transformation. And that would mean instead of just using a simple matrix as your projection, you could do something more complicated and just literally have a small neural network be the thing that generates your college. Ultimately, I don't think people do it because there's no need to. Because what's the difference between having a more complicated projection scheme here or just doing another transformer layer? If you think about it, they kind of end up being the same, and you might actually want simplicity in the training for